So we come now to the Lorentz transformation. So let's set this up. Got a lot on the board here. We're going to go through it as usual, bit by bit, but I want to expedite matters and get some of the key things up here so I'm not just wasting time, as it were, writing on here. We'll have a lot of, this is probably the most mathematical series of video clips we'll do. Again, most of it is just algebra. It takes a little while to get through it, so we'll break it up into several video clips and make hay slowly, as is usual. And for those of you who, the algebra is very familiar to you, then you can obviously speed things up. So the Lorentz transformation. Let's just remind ourselves about Bob and Alice here. This time we'll have Alice stationary, Bob in the spaceship going at some velocity v. Of course, each of them have their frames of reference. Remember the props we've used before in terms of each of them, perhaps a spaceship, the lattice of clocks. So we can imagine Alice with a lattice of her clocks all synchronized, Bob with a lattice of his clocks all synchronized. Remember, in Bob's frame of reference, he's stationary. Alice is moving in the opposite direction behind him. Alice, in her frame of reference, she's stationary, and she sees Bob moving with velocity v in that direction. At the start, when Bob passes right by Alice, we'll assume that they start their clocks at that point. And so TA, T sub A equals 0, T sub B equals 0. And we'll also have the origin for their measuring systems also to be 0 at that point. So everything matches up there. We'll get on to this in a little bit, this later at time T sub B, where we get a flash of light going on. But here's the basic question we want to try to answer, and that is, given the coordinates, space-time coordinates of an event in Bob's frame of reference, so xb, yb, zb, and some time T sub B, what would the coordinates be for Alice, xa, ya, za, and ta? In general, we'd like to go back and forth between the two coordinate systems. If Bob measures something, it says, hey, I saw a flash of light, and it was at this location in my frame of reference, and this time, we'd like to have a relatively simple calculation so we can find out the coordinates of that flash of light in Alice's frame of reference. Clearly, we can sort of work through examples we've done before, but we don't want to have to do that every single time to work through the details, so it's nice to have a formula, and that's what the Lorentz transformation is going to give us. It's going to be similar to the Galilean transformation that we worked on before, so let's recall that. Simply that if we have two frames of reference in relative motion with respect to each other, inertial frames of reference, so constant velocity motion, and we'll use, again, Bob and Alice here, so Bob moving to the right, Alice stationary. If Bob measures something at coordinate x sub b and time t sub b, then Alice can find out where that is in her frame of reference by taking the x coordinate of Bob and multiplying by v times his time to find that out. And note the plus sign here. Think it makes sense intuitively because we know Bob is moving to the right. So if Alice is standing here, as Bob moves on, then if he measures something at 0, at his xb equals 0, we know Alice's measurement is going to be farther on in the positive direction because that's the direction Bob is moving with respect to Alice. And so it'll be whatever position Bob measures something at plus essentially the distance traveled by Bob in that given amount of time until he sees the flash or whatever happens to be. And then, of course, the y and z dimensions remain the same. They're not changing, and we essentially have ignored them in most of our examples, but to be complete, you could put those in here. And a key thing for the Galilean transformation is time was the same in both frames of reference. Now we know, we'll get over to the details of this in a minute, but we know right away that from Einstein's two postulates, we derive the fact that time dilation occurs and length contraction as well. So we know that this thing in particular, the time relationship here, is not true for the special theory of relativity when you get, certainly when you get higher velocities, but in principle for any velocity, as long as you have that velocity between frames of reference, there is an effect such that TA and TB are not equal. Again, as we've mentioned, it's so small usually in our ordinary everyday world we don't notice it, but if you have very precise clocks, it is possible to measure that difference. So we know that the Galilean transformation can't work. We'd like to have something like this that works with special relativity. So that's our goal here. We'll get back to the stuff over here in a minute, but let's set up situation for Bob here and Alice. And what we want to do is later at time tb, so they pass each other at time t equals 0 essentially, and then later at some time tb, according to Bob's clock, he sees a flash of light right at his cockpit. So in other words, that is occurring at xb equals 0. Because remember, he's carrying along his lattice of clocks with him, his measuring system with him. As far as he's concerned, he's at rest, and Alice is going backwards there. And therefore, if he sees a flash of light right next to his cockpit, the x location for him, x sub b, would be 0 at that point. And we actually could then figure out where Alice sees that flash of light and what time, given the x location for Bob and the time t sub b for Bob. We could figure that out for Alice. In particular, one thing we'd use would be our time dilation equation. TA equals gamma TB. Remember, Alice is observing Bob's clock moving, and therefore time dilation will occur for Alice observing Bob's clock. Alice will see Bob's clock ticking more slowly and running more slowly, right? That's the whole idea of time dilation. Bob does not see any difference. His clock is working just fine as far as he's concerned. It's Alice observing the moving clock that has this Lorentz factor, gamma, involved in there. And of course, gamma 1 over square root of 1 minus v squared over c squared. Remember how we derived this? We derived this using the light clock, and didn't make a big deal of it at the time because it wasn't important then. But this was derived for Bob's location at 0. Okay, because remember in the light clock, we have it here, and we have our light bouncing back, going up and down. That's what Bob is seeing on his light clock. The light motion going up and down, the light pulse going up and down, is occurring at the same place all the time. Bob's just, he's got his clock right next to him there. It's Alice observing it, of course, moving along, so that as Alice sees it moving here, we'll squeeze this in, we get the familiar triangle effect. So Alice sees it going like this. But to Bob, all this is happening at xb equals 0. So our first time dilation equation really assumes that everything is happening at xb equals 0 for the person who is moving. And the Lorentz transformation we want, though, needs to be more general than that. Because, again, back here at the flash of light example, if the flash of light occurs right at xb equals 0, at Bob's cockpit there where he is, then fine, we can use our basic time dilation equation. But he might see the flash of light out here someplace. And therefore, we'd have a more complicated situation. And this will still be true in a sense, but we need to actually get a more general form of it. And we will see that once we get to the end result here, the Lorentz transformation. We'll have some equations here that in the case for xb equals 0, when whatever is occurring, the flash of light, say, is at Bob's location, then this will still be true. But we're going to get a more general form of this type of relationship. Now, we also know, just as a reminder, the invariant interval equation. And this is true in general. And so this will be very useful for us to derive the Lorentz transformation equations that we want here. And again, it's just algebra, but it's useful to work through it so you can see where it comes from. It's not just magic. It doesn't appear out of thin air or anything like that. But it's a sequence of logical steps building on what we've done before. So we're going to start off just by considering, actually, in a minute we'll get to, in a couple minutes, we'll get to the flash of light out here at a general location. But let's just do the flash of light first at Bob's location there. So that's where we're going to head here and see what we get. So that's our general question. That's our goal. We want to, again, be able to transform back and forth there. And so we're going to start here with a couple things we know. Okay, so here's the situation again, later at some time tb, flash of light. We know, therefore, that flash of light occurs at xb equals 0, okay, at Bob's cockpit. What else do we know about that flash of light? Well, where does it occur for Alice? Well, Alice sees Bob traveling along at velocity v. We know we set up so they measured everything, the origin from when they were right together a little while ago, and then Bob traveled on. And so we can also say, if we say, just to indicate, this is the location of the flash to Bob. The location of the flash to Alice is simply going to be the velocity, relative velocity, times whatever time she sees on her clock, just v times ta. Okay? Now, here's the key thing. What is ta? Remember, we want to have sort of Bob's coordinates on one side and Alice's coordinates on the other. And so Bob measures the flash at time tb. We'd like to know, somehow write ta in terms of tb. Now, in actual fact, this is a case where our time dilation applies because we're talking about a situation where the flash is occurring right at xb equals 0 for Bob, sitting right next to him there. And therefore, we can just actually put this in here. Ta equals gamma tb, so this is going to equal, just put gamma tb, and then I'll put the gamma in front, because we often like to write the gammas in front. Gamma v tb. Okay, so that gives us some good information there. Therefore, if the flash of light occurs at xb equals 0 at some time tb, so Bob records some time tb on his clocks, then I can find out the x coordinate in Alice's frame of reference for that flash is just gamma times v times t sub b. So if Bob gives me that answer, or I take a photograph and look at his clock, observe his clock at that point, I can figure out the location in Alice's frame of reference as well. And then this would give me the time in Alice's frame of reference. Let's also, though, get this in another way using our invariant interval equation, because we're going to use this more here in a few minutes. And so just to show you that it does work the same way, let's just rewrite this. So we've got c squared ta squared minus xa squared equals c squared tb squared minus xb squared. That's our invariant interval equation. That's good for anything, basically, given ta, xa, and tb and xb for a given event or distance between two events. In this case, the distance between the events will be our origin point when they pass each other, and then a while later the flash occurs, and Bob measures it again, t sub b and x sub b, and I want to be able to get the t sub a and x sub a from that. So what do we know here? We know, applying it to the flash of light right here, the flash of light occurs at 0. So that means this thing right here is 0. We don't have to worry about that. And so we're left with ta, xa, and tb in here, and of course c being the speed of light. And then let's also put in this, vta for the flash of light. Again, that's Alice's distance for the flash, because it's just the velocity of Bob times how much time elapsed on her lattice of clocks. And so let's plug this in here for that. So we're going to get c squared ta squared minus v ta squared, just plugging that in, equals c squared tb squared. And advantage, of course, of these formulas is you just sort of, once you set it up correctly, you sort of crank through it here. And so note that, well, we'll do every step here, c squared ta squared minus, this becomes v squared ta squared equals c squared tb squared. And when I think about that, now I just have the times in there, just ta and tb. I've got a ta squared in both of these terms here, so let's factor that out. So that gives me a ta squared c squared minus v squared equals c squared tb squared. And now we're going to bring it up here so we have some more room. And so come up here. Now what I can do, let's divide each side by the c squared minus v squared. Okay? So I can write this as ta squared equals c squared over c squared minus v squared tb squared. See what I did there? I just took this and really put it over on the other side of the denominator. Divided each side by this. So I got 1 here and c squared over c squared minus v squared over here times the tb squared. This becomes, for those of you who are up with your algebra, you might want to play around with this a little bit, see what we get here in a minute. So pause and if you want to do that and see what our final answer is going to be. It's going to be very familiar, but let's see what we get here. So let's do this. Let's factor out a c squared in the bottom. So I can write c squared times 1 minus v squared over c squared times tb squared. Okay, the reason I did that, well, first of all, I can do that. I've got c squared minus v squared, so I pull out the c squared, and I've got v squared over c squared here. So this and this, they're the same things. The reason I did that, as you may see by now, is I can cancel my c squareds there. And so, where does that leave us? It leaves us with an equation like this. We get ta squared equals 1 over 1 minus v squared over c squared tb squared. Now we take the square root of each side. All our TAs here are assumed to be positive. We're looking at positive times, so we don't have to worry about when we're taking square roots plus or minus signs, as some of you may remember with that. So we get TA equals 1 over the square root 1 minus v squared over c squared tb. In other words, square root of ta squared is ta, square root of tb squared is tb, square root of this is this, and this should look familiar, I hope, right? This is gamma. So really what we've just shown is TA equals gamma TB. We started with this equation, with the invariant interval equation, and the fact that we are looking at a flash of light at xb equals 0, because remember, so we plugged 0 in here, and then worked through the algebra, and lo and behold, what do we get? We get our time dilation equation. TA equals gamma TB. So that's good news, because if we didn't get that, we would have made a mistake someplace along the way, either here or perhaps in our earlier derivation of the time dilation equation using the light clock. Okay? So therefore, we say, okay, we've got this equation. That means Bob measures T sub B, and now Alice can, given that value on Bob's clock, again, take a photo flash, our old photo principle idea, take a photo of that, could see what's on Bob's clock. And if she, on her lattice of clocks that was at that location as well, took a photograph of her clock, this is what would be the reading on her clock. It'd be whatever was on Bob's clock times the gamma factor times TA. And of course, gamma is always greater than or equal to 1, and so forth. And so you get the time dilation effect there. So given T sub B, then we know what T sub A is, but what about XA? What's the X location in terms of Alice's lattice? Well, I just erased them a minute ago, but remember we had this. We had XA simply equals V times TA. Now it's just the velocity of Bob times the time, elapsed time on Alice's clock. So she's watching Bob go by with velocity V. And therefore, this just is TA equals gamma TB. And so we can plug TA into here, and we get, this is gamma V TB. So that's XA. So now we have our two, sort of highlight them here. We've got that and that. That's a form of the Lorentz transformation for the case where the event is occurring at xb equals 0. Okay? And as we set up with the origins like that, which is standard procedure to set up the origins like that. If they're not set up like that, you can always, you can start your clocks at the proper time, or you can adjust the clocks. You can also adjust the clocks back and forth if you want to get a 0 point at that instant to have everything match up, and both Bob and Alice have their clocks at 0. Later on, of course, if Bob is moving, then they're not going to be synchronized anymore, as we talked about with the relativity of simultaneity. But here's the Lorentz transformation equations for this case where the flash of light is occurring at xb equals 0. In other words, Bob says, hey, I measured a flash of light. It was at xb equals 0 and tb equals something or other. And then Alice could immediately say, okay, I know where that location is in my frame of reference. It's going to occur at time ta equals gamma tb. So Bob tells me t sub b. Alice then calculates t sub a. Got that? And also given t sub b, Alice calculates x sub a as gamma v t sub b. And so again, that's sort of a limited form of the Lorentz transformation for this special case. What we're going to do in the next video then is consider the case of what happens if the flash of light is not here as Bob measures it, but it's out here someplace at some general value of x sub b. So he'll have some value of xb for the event, this flash or whatever it happens to be, and the value of t sub b. And then we want formulas sort of like this, they'll be slightly more complicated, that Alice can use to figure out the time t sub a of that flash or event out here and the location x sub a. So that's coming up in the next video clip.